All right, welcome back everybody for the final part of this particular lecture on power. I just wanted to share with you some of the enjoyable Calgary weather we're having. So we've gone from sunshine to kind of a snow squall here. It's a pretty common sort of thing in this part of the world, and just as another sign that winter is on its way. It's Canadian Thanksgiving today, so I guess we should be thankful regardless, but still, sometimes it's a little hard to deal with. Anyways, I'm staying warm in the car. We need to wrap up this lecture though by finally answering this question, like how many subjects should I run in my experiment? And this is a question, as I've said before, that's suitable for power analysis because you want to answer it before you actually run your experiment. So we've talked about this before, but we have basically 4 or 5, depending on how you count, factors that are all interrelated. So there's the power measure in general, which we just found out how to calculate if we know the other 4 parameters here. So there's power, which is 1 minus beta. There's alpha, which is the percentage of false alarms you get from your experimental setup. And then there's the sample size, which is the number of items in your sample. And then we have the actual mean and standard deviation, which we can kind of combine together to calculate what's called an effect size, which is what we talked about at the end of the last lecture in this set. So it turns out that if you know, counting this way, we're looking at 4 different values, and this one should be in, I'm not going to be able to change that. And if you know 3 of these, you will be able to calculate the other. So we talked about that before, like if we know 2, 3, and 4, we can calculate power. But now we want to know 1, 2, and 4 just so that we can calculate 3. And as I mentioned before, even when we're sort of just calculating power, you won't know what the actual mean and standard deviation of your population are before you run the experiment. So even if you're using 1, 2, and 4 to calculate 3, or 1, whatever the case may be, you're going to have to make a guess about what number 4's value it actually is. So we have conventional criteria for alpha and power, 1 minus beta. We want our analysis to tell us what n ought to be, and we have to run the experiment to find out what the effect size is based on the actual mean and standard deviation. So we don't actually know what this is, so we kind of have to ask for help, as I mentioned before. And basically the way we help ourselves out is by making an educated guess. As always, this is the name of the game in social sciences, I guess you could say. So you simply have to take a shot in the dark as to what the effect size is going to be, but conveniently there's different ways you can do that in a reasonable fashion. So I'm going to go back to some of the Cohen reading here. So in case I didn't mention this before, there is a reading I posted from Jacob Cohen, not BBC News. But if you go to the readings tab here on the homepage, there's one article here on it's the effect size. Hopefully this is still live. Yeah, I'm sorry. That's a dead link. I got to get rid of that. And there's one here from Jacob Cohen, which is not dead, which, as I mentioned before, is from the 80s, I believe, but it goes through the basic concepts of power analysis and talks about how to estimate effect size when you don't have any data yet that's relevant to your problem that you're trying to address in your experiment. So one way you can make a guess about effect size is by looking at previous related research results in the literature. So like I said before, we could say estimate that the mean VOT of unaspirated stops is 0. That's a reasonable guess. There's a number of good studies out there that look at like how VOT changes in different languages. If you're making a guess about like what the mean VOT of aspirated stops are in a language, there's a number of different possibilities. It could be like 60 milliseconds, it could be like 120 milliseconds, it could be a variety of different things, but you can look at previous studies that have tried to estimate those parameters and borrow their results for your own power analysis when you're prior to doing your own experiment on the same thing. Yeah, so as usual, do your homework before you do your experimental work. It'll help you out a lot. It'll make your life a lot more efficient that way. You could also look at the results of pilot data, and we're going to do that here at the end of this little lecture, or this final part of this long lecture, to try to learn how to put these ideas into practice for our own purposes. So yeah, I always recommend if you are going to do an experiment that you should run a pilot. Mostly for methodological reasons. It will help you find out what works in an actual experimental setting and what doesn't sort of fly with subjects. But it will also give you a chance to try to figure out how to analyze your data before you have to analyze data from the real thing, right? So you can get a small batch of data and say, well, I'm going to do this sort of transformation to it, or run this sort of test to get my, beloved p-value at the end of the day. So that's one thing you should always do, because you can clean up a lot of mistakes before you get into the real thing. And you can also get an educated guess about how many subjects to run out of the same process. Number 3 is you could have some sort of ingrained expert knowledge about the problem. I think that would apply to sort of the 0 milliseconds VOT for unaspirated stops. That's just kind of how they're defined in a certain sense. Or, what have you, some estimate of format values for a language or whatever. But this is, again, trying to make some sort of educated, reasonable guess about what to expect. But lastly, if you can't get access to any of this sort of background knowledge or experience, you could resort to Jacob Cohen's own guidelines about what effect sizes you can expect to get from your experiment. And remember, these are referring to Cohen's d, or that standardized effect size. So 0.2, he said, would be a small effect size. 0.5 would be average, which is kind of a nice little number. If you think of 0.5 as like average between 0 and 1, that's an average effect size. And then 0.8 is large, based on his analysis. And, it's a bit funny to think about, because why should there be these generalities at all in effect sizes? Because people can set up their experiments any way they want to, really. But this is kind of averaging across a whole wide range of them that have been set up in different ways. But basically, they reflect the difference between sort of the mean values of two different groups, or the mean value of some set of data out there, and whatever people hypothesize the mean value would be. And then it's normalized over the pooled standard deviation, or pooled variance from those two groups of data. And then it winds up kind of ranging from 0 to 1, where the closer you get to 1, the larger the effect size seems to be, and the closer you get to 0, the smaller it seems to be, with 0.5 somewhere in the middle. So Cohen's numbers from small to large effect sizes come from a meta-analysis of the results of thousands of studies. So he did the homework for this so that you don't have to. And if you read that article that I just linked you to a second ago, he talks a fair amount about IQ, intelligence quotient, in it, for better or for worse. I think there are reasons to be skeptical about that measure, which I won't go into here, but one thing you might not know about it is that it's supposed to be normally distributed. So you might know as well that average IQ is 100, and I believe the standard deviation is supposed to be 15. So if you have like an IQ of 115, that means you're one standard deviation above the mean, which, if we do the grunt work on that, I think that would mean that you're smarter than 84% of the people in the world, or something like that. And 130 would be 2 standard deviations, so on and so forth, all the way up the line. Cohen claimed that if you look at the IQ differences between different groups of people, the mean IQ difference between twins and non-twins, so siblings, I guess, within the same family, would be 0.2. So presumably these people would have similar, experiences in their lives as growing up in the same family, but this sort of refers to, I guess, sort of what inherent biological differences there are in IQ between otherwise related people. So it's not that big. It's a small effect, but it's there. 0.5, according to Cohen, would be the mean IQ difference between clerical and semi-skilled workers. And 0.8 would be the mean IQ difference between PhDs and first-year college students. I guess we all have PhDs here, or are trying to get one, or maybe not. But either way, supposedly, if you're a grad student, or I guess faculty or something like that, and a first-year college student, there's a big difference in your intellectual capabilities, according to Jacob Cohen. But maybe that just kind of gives you a rule of thumb for how, what an effect size kind of looks like in terms of its magnitude. And I have a little disclaimer here that a PhD is not the same thing as a high IQ. And to be honest, I feel like the smartest people I know in life are not in academia and do not have PhDs. And I think maybe that's one piece of evidence for why they're smart. But I won't get into that either. Instead, I will go into the work of some of my students who are striving to get a PhD. The first is from a student of mine, Jacqueline Jones, who ran a study about 10 years ago for her honors thesis at the time. And it was a really cool, interesting design for a study. And I'll load up the data here in R before I tell you a little bit about it. But basically what I'm going to get from this R command is the pilot data from the initial experimental run that she conducted. But what she was looking at, I can't remember the details, it's so long ago, and I haven't looked up the results of the pilot for a while, but she was looking at how well people could understand different synthetic speech voices with an eye towards trying to figure out whether people could sort of become familiarized with certain synthetic speech voices in a way that would help them understand the familiar voices. And I'm not explaining this well, but you can create synthetic speech using different sorts of algorithms, but even within a certain algorithm, you can create different voices like male and female or individualized voices, right? And her idea was like maybe if you become sort of attuned to certain individualized voices within a certain type of synthetic speech, you can understand that speech better. So, some female individual A or female individual B, maybe you learn female individual A's voice well, and you can understand her better over time. And this is just like her first attempt to try to understand how that all worked. And I can show you what sort of results we have here. So this is, she was having people listen to sentences produced in different types of synthetic speech. There was synthetic speech type 1 and synthetic speech type 2. And these were the reaction times. So they would listen to a sentence and then they would type in what they thought the voice said. And we measured reaction time in milliseconds. So like speaker or subject number 1 took 9.5 seconds to respond to synthetic speech type 1, and then that person took almost 14 seconds to respond to synthetic speech type number 2. So she was just measuring, are there differences in how quickly people can understand these types of synthetic speech. So we can look at the overall kind of effect that she got here. So this is 20 people, I think, probably not 20 responses. These are 20 different people listening to sentences in one type of synthetic speech or another. And if you just look at the means, the raw means, it looks like they're able to respond faster to synthetic speech type 1 than they are to synthetic speech type number 2. So about 8 seconds for the first type and 11 seconds for the second type. So that's 3 seconds to type in what you thought somebody said in a sentence. And that kind of seems like a fairly long time, right? So 1, 2, 3, that takes a while. Is it statistically significant or not, though? So if we just look at going back to this concept of effect size, if I'm just calculating the raw or unstandardized effect size, I get this effect size of almost 3 seconds. So 2,759 milliseconds, 2.759 seconds. But if we want to standardize that measure, we have to do so with respect to the pooled standard deviation between the two samples. So I'm going to, I call this pooled standard deviation, but it is based on the equation for pooled variance, which I showed you a few lectures ago. So I'm calculating that pooled variance, and then what I'm going to get out of that is I'm going to take the square root of that to get the pooled standard deviation. So if I just look for that number, I get about standard deviation, a pooled standard deviation about 2,500 milliseconds and change. And then what I can do is divide my raw or unstandardized effect size by that pooled standard deviation, and I get a really large effect size, it turns out, of 1.08. So according to the Cohen guidelines, 0.8 was a very large effect size, or a large effect size. I guess this is a very large effect size, 1.08. So that's bigger than the IQ difference between PhDs and beginning college students. So I don't know, maybe we're getting into high school here, or some sort of super nerddom on the other side. But either way, that's how you would calculate it, and this is just using this basic set of raw data from Jacqueline's pilot. So that's just looking at effect sizes. We still want to answer this question about how many subjects we should run, though. So how do we do that? And I'm going to point out again here that, as usual, we can let R do the difficult work for us. I'm just showing you how to do the difficult work so you understand where the numbers are coming from. But to estimate the number of subjects that Jacqueline should have run in order to get a significant effect in her study, it probably won't be that many, right? Or I guess maybe this is going to estimate like how many items she has to run if these are all just individual responses from two different, no, I guess these are all, these are all different subjects. I can't remember exactly, but it'll tell you how many rows basically she should run in her experiment, how many items in each sample to get a significant effect. So this is how you run that command in R. After 40 slides and maybe more than an hour and a half of lecturing, we're finally answering the question. So the command is power.t.test. And then within these parentheses, you have a number of different parameters, all of which we've talked about already. So delta is this raw effect size here. You just put in that difference into the command. And if you really wanted to, you could put this whole equation in there if you wanted to make it more general, but we'll spit out the specific numbers so you can see where it's coming from. And then the standard deviation, which is going to standardize that effect size. So that's coming from here, goes into this part of the command. And then the rest of this is conventional. So significance level is alpha, and that's 0.05, then power is 0.8. And then if I hit return, what it's going to do is going to spit out a whole bunch of stuff. Basically, it's going to spit out a number n of items that should be in each sample. So this is going for a 2-sample t-test power calculation. And you can do this with different kinds of t-tests, like 1 sample and like 1-sided or 2-sided, that sort of thing. But the default is 2-sided, 2-sample, which is, again, the kind of t-test you're most normally going to run. These values are what we put into the model, and then it spits out this new value of n and says basically 14.4. So that's the number of items you need to have in each sample to get a significant effect with this amount of power ahead of time. This calculation basically says run 14.5 subjects, and of course you can't run a half a subject, so run at least 15 subjects in your experiment. And that's a reasonable number to run to get a significant effect if there's one to be had, basically. So that's kind of the answer to that question. In other words, is 15 for Jacqueline's raw set of pilot data. I'm going to show you how to do this not with a 2-sample test, but with a paired sample test. And like I said, you can do all sorts of different options here, but this is how you indicate to R that you want to run a paired sample test, type equals paired at the end of all this. And then when I do this and I say that there's nothing different between these two groups other than just like the synthetics, or just the, I think this would be, the type of synthetic speech, RT1 versus RT2. And we have the same subject sort of giving responses to both. We pair it that way, and we find that we can actually run far fewer subjects to get a significant effect by using simply a different statistical test. So in this case, I would only have to run 8.8 or boost it up a bit to 9. I'd only have to run 9 subjects to get a significant effect. Or I'd plan on running 9 subjects and reasonably expect to get a significant effect if there's one to be had. So again, we're running this analysis before we do the experiment. So this basically gives us a number to say run. And then, again, according to the rules of the game, you can't sort of cheat on that commitment once you've started in on it, right? So if you do the power analysis and say, I'm going to run 9, or let's say I'm going to run 10, because that's a nice round number, then you run 10 before you do any stats on it, right? And then at that point, you're like, well, based on the initial analysis, I can expect to get significant effect if, there is something going on in the data, and I look at it and I get my p-value and I'm just done. I don't just keep going until I finally get that significant effect. I just commit to it and be done with it. That's the fair way to run the methods in this case. And I will mention again, though, this little note on the bottom of the slide is if you can run the stats in a more clever way, that may help you do less work for your honors thesis or whatever you're doing this for. And so you can get your thesis done quicker or your paper out the door more quickly and off to the races on the next project, simply by being clever about how you run the stats. I will show you some other data, and we can kind of work through how to calculate the same numbers for it. I don't have all the answers in this slide or set of slides in the PowerPoint, but I'll show you how to do it here in R. But this is around about the same time in history, about 10 years ago. I had a different honor student at the time named Sarah Greer, who was looking at whether daughters use more creaky voice than their mothers. So this is kind of an idea that at the time, Darren Flynn and I had talked about like, well, again, experience might matter in terms of, generational differences in the speech variables that people use. So maybe the best way to control for that is by having mothers compared against their daughters. And we were looking at female speakers of English here for different reasons, but basically with the idea that young females are using a lot of creaky voice, but are they using more creaky voice than the previous generation of English-speaking females did? So we had mothers and daughters come into the lab, or Sarah had them come into the lab, and she had them talk to each other in a number of different speaking tasks, which was kind of cool. And I'll show you her data. It's basically, she transcribed a huge amount of conversation and speaking tasks from both mothers and daughters. So we've got different pairs here. There are 5 pairs of mothers and daughters, denoted by M and D. And then she had them doing reading tasks, and she had them doing conversation tasks with one another. And these numbers are just like the percentages of how often they were using creaky voice or maybe breathy voice as opposed to modal voice. So yeah, there's some complications you get into when you start using percentages, but we'll just pretend they don't exist for now. And try to run power analysis for a t-test with this data. So we'll extract out the daughters' data first, and then we'll also look at the moms by themselves. Yeah, and I really should have figured out the correct answers here, but before I ran into this, but we'll just fly with it as it comes. But if you run a t-test where you look at how often people are using creaky voice overall in this experiment, and we compare it because the only difference between each person in the pair is that whether one's a mother and one's a daughter. Run a t-test for how often they're using creaky voice, we don't get a significant difference. Yeah, so one thing I didn't look at here, and which is not reporting directly, is what that overall percentage is for both groups. So the daughters were using almost 20% creak in their voice overall, and the moms are using about 13%. We can look at it in conversation using this paired equals t option because we think that paired samples t-tests will give us more power overall. And we still don't get a significant effect when we run that test, but we can take a look at the means and see if we're maybe getting a little closer or what they kind of show us overall. And we get a bit of a boost for the daughters there in conversation, and for the moms we get a bit of a drop off. So yeah, it's looking like this is heading in the right direction, but it's not significant. So again, I guess to talk about the rules of the game, it may seem like this is cheating a little bit, but we're just saying like we ran 5 pairs of mothers and daughters just to try to like work out the kinks of the methodology, and also to get a sense of like how many subjects to run and how to analyze the data. If you're doing that ahead of time and saying this is just my pilot, I'm going to run just like 5 pairs of people and try to figure out how many pairs I should run overall, then it's okay to look at the data at this point and try to answer that question. But then you need to set off like this data from the official experiment and say, well, if this tells me I need to run 20 pairs, then I'm just going to go ahead and run 20 new pairs of mothers and daughters and analyze that data independently. And whatever it tells me is whatever it tells me. So what I have questions here, like how many pairs should she run and what sorts of effect sizes is she looking at in her initial data. And we kind of have a sense of what the effect sizes are already. I'm going to borrow the code, though, from the Jacqueline analysis to kind of give you a sense of how it would look here. I think maybe I'll just do it for the conversational data because it looks like that's a slightly bigger difference. So our unstandardized raw effect size is 0.09, 9%, whatever that means. To try to figure out what it means, we need to come up with a pooled standard deviation, which involves the variance of both groups here. And once again, I'm losing my voice. And kind of the difference here that I didn't mention before, which is kind of important if you want to do this for your own homework, say, is this number 19 here. So there were 20 data points in Jacqueline's data sets, and then 19 is basically n minus 1, 20 minus 1. That's the degrees of freedom for Jacqueline, and then 38 is n minus 2. If you go back to the equations for, or the equation for pooled variance, you'll see those pop up there. But we can do it this way for Sarah. So she's got a pooled, sorry, I am losing my voice, pooled standard deviation of 0.068. So once again, this is going to be a standardized effect size of greater than 1. So our prospects are looking good there for getting a significant effect by running the whole study. And what I will do to try to spit out a number of n for this data, how many subjects should she run? And we'll pair the t-test to try to help ourselves out a bit. Instead of just using the raw number here for delta, I'll do it this way and put that in parentheses. So this is just going to be my raw effect size. And then for standard deviation, I'll put this pooled standard deviation and leave everything else the same and hit return. And this tells me my n needs to be 6.69. So basically she was almost there with the pilot study because she needed to run 7 or more pairs of mothers and daughters to presumably get a significant effect. And it looks like there's probably something going on. We just didn't have enough data. We didn't have enough power in our samples to get it. But again, like I said, you can't just like take those first 5 and add 2 more pairs to them and then run the analysis again and say, oh, now I got my p-value. Just set that initial batch of data aside, run a whole new group of 7 or more in this case, and then see what you get from the stats. Couple crucial things there is that to be on the safe side, you kind of want to run more subjects than is the raw minimum recommended by your power analysis. But in theory, you could say, well, I'm going to run 7. And according to this power calculation, I should be able to get what I'm looking for if it's there. But I would say probably, run like 10 or something, just a nice round number. And, if it's there, it's there. And if it's not, it's not. Don't kill yourself running too much more than this. But, you don't want it to kind of come to like, a p-value of 0.051 or something that, seems like it could have been there. And then you always have this question of like, well, did I just need to run more anyways? Just a little bit more than the raw minimum will kind of put you on the safe side and put those doubts out of your head if you can wind up with something close. And then your work will hopefully be appreciated by all and not feel like you just spent a lot of time on something that didn't amount to what you hoped it would. I'm not going to say anything further about that now, but this is basically how you answer that question. And it's funny because, Sarah, for her master's thesis, went on to do different things. Jacqueline did too. And so these both kind of wound up just being pilots that were interesting honors theses to read, but we kind of didn't sort of verify with a full-fledged complete study based on these sorts of analyses afterwards. So they're still kind of hanging out there. The research questions are still interesting, but, that's the name of the game. We can't do everything we want to in our academic lives, no matter how interesting that might be. But I'm going to call it a day on this lecture because it's definitely long enough by now, and hopefully it all makes sense. But if it doesn't, you always know where to find me, and I'll see you next week for wherever we head next. See you then.